We're up and running.
Thank you again, Dave. This water resource vision, ARS, basically lead U.S. research agency, as I said earlier, investigating the effects of water resource on agriculture and the water impacts of agriculture on water resources. I mentioned this earlier in my introduction. Scientists write detailed 5-year action plan, so the NP211 national program to address specific hydrologic issues facing stakeholders. But USDA needs an overarching long-term vision for water research. So the purpose of this exercise is to develop this vision for 2050. So we invited leading USDA ARS research scientists in facilitated virtual workshops over the last year. We have been a number of meetings. Okay, yours. Okay. Identified, challenged, and drafted goals and something. Okay, and then we formed writing teams around key components of the draft vision, which you will hear more later. And also we synthesized into an executive summary. And today we present to our partners for feedback and collaboration on developing this water vision document. So next, you'll hear the challenge identified by my colleague, Dr. Daniel Peck. Daniel.
Thank you, Dr. Sagai. It is such a pleasure to introduce the draft water research vision to you all today. And our very first step as a visioning team was to reflect on the water challenges of today and the future. And through team discussions, kind of two major drivers of current and future challenges emerged, and that's climate change and increasing demands on our water resources. Against the backdrop of these two major drivers, we identified 4 broad categories or types of water challenges: water scarcity, and then on the other end of the spectrum, water everywhere or overabundance, water quality, and then water as a really integral part of our cultures, our economies, and with really important implications for equity and justice. So the map here shows some example case studies that ARS is working on for each type of these challenges. Regarding scarcity in the map, you'll see some areas highlighted in black, and particularly kind of 3 main aquifers in the US. But these are just examples. Water scarcity isn't just a challenge in the West, but also in the East, where it's not always just a simple water volume challenge. Sometimes it's a water timing, a location, or a management challenge instead. For water everywhere, if you look at the map, you'll see that there are some rivers highlighted kind of in a dark blue color, such as the Missouri and Mississippi River basins. And so those are just a few examples of places where water everywhere is the challenge. For water quality, our case studies are represented here with raindrops. So you can see those up in the Great Lakes and the Chesapeake Bay, and again down at the mouth of the Mississippi River. And finally, water, again, it's part of our cultures and our economies, and that's not shown here on the map, but obviously water runs through everyone's lives every day. And so as scientists and stakeholders, we need to work together to manage these challenges. We need to recognize that water is valued in really diverse, evolving, and often conflicting ways, and that we have to account for this when we're co-developing solutions or when we're trying to help build society's capacity to address future challenges. To do this, we want to work in transdisciplinary teams. And by definition, this means working collaboratively to actually learn from each other, blend our diverse knowledges and experiences to develop new path-breaking approaches, insights, and solutions. And this is different than business as usual. It's different from just a multidisciplinary approach. In the past, we had a tendency to kind of retreat to our disciplinary corners. And yes, we were working on the same shared problem, but we would go off in our corners and work on them individually and then come back together at the end and see how our parts fit together. With transdisciplinary teams, we try to stay at the table together throughout the entire process, working side by side, learning to speak each other's disciplinary languages so that we really truly can blend our knowledges and our approaches into something entirely new and, again, path-breaking. We feel that ARS is really uniquely positioned alongside all of you, our partners, to bring scientists from all of these different disciplines together, as well as with producers and community members to discuss, question, and explore these water challenges together. So with these broad approaches and challenges in mind, I'd like to share next a high-level overview of our draft water research vision document, which we've invited you here today as our valued partners to provide input and feedback on. So in this diagram for our water research vision for 2050, it's organized into several sections. And again, today you'll have an opportunity to provide input on these different sections through a series of breakout sessions. The vision begins, of course, on the ground with you, our valued partners and collaborators. And that's represented in this diagram, kind of down in that lower left-hand corner, the first and most important block in the foundation for our vision. In partnership with all of you, plus our mutual stakeholders, we will use collaborative research approaches, that middle foundational block, and innovative science and management tools over there in the bottom right corner to form and nurture these transdisciplinary teams, kind of in the middle of our diagram, who are going to represent diverse and inclusive water expertise and knowledges. Together, these transdisciplinary teams will collectively help achieve our expected research outcomes, which are up at the top of the diagram, to address society's most critical water challenges in ways that positively impact our stakeholders. So with that overview, I'm going to pass the baton from my team, which was the current and future challenges section, to the partnerships and collaboration team. And that's going to be represented today by Dr. Michelle Reba. She's a research hydrologist and acting research leader at the Delta Water Management Research Unit in Jonesboro, Arkansas. So thank you, and take it away, Michelle.
Thank you, Jenna. That was great. I want to start with a quote from the author Ken Blanchard that states, "None of us is as smart as all of us." This sentiment is really echoed in the partnership and collaboration section of the Water Resources Vision, which states, ARS engages collaborators and partners in research that has long-term focus, is both place-based and at a national scale, and solves complex agricultural system water issues using a transdisciplinary approach. The partnership and collaboration section of the vision highlights collaboration with multiple entities, federal and state agencies, producers, universities, private companies, NGOs, just to name a few. There are two specific items discussed in the incorporation of technology and collaboration, how we can do that better. And also we talk about the co-location of ARS units with or near university collaborators. The section also uses GrapeX and OpenET as an example of partnership and collaboration. There are 10 separate and very specific approaches described as to how ARS will strengthen partnership and collaboration through streamlining of agreements, training of incoming scientists, increasing engagement with underrepresented communities, and leveraging networks, just to name a few of the 10 that are described. With this high-level overview, I want to share an example of how ARS is working with partners to address water supply or water scarcity issues through managed aquifer recharge. Managed aquifer recharge is a broad term that includes various engineering methods designed to increase the flux of water from the surface to an aquifer system. This can be done with the aim of storing water for later use, recovery of groundwater levels, natural treatment of recharging waters, and even inhibiting saltwater intrusion in coastal systems. Recharge can occur through infiltration basins, infiltration galleries, dry wells, riverbank filtration, or direct injection. The best strategy to employ is really a function of site characteristics and available source water, and also governing regulations. I'm showing images here of 4 ARS-led MAR projects. All are driven by water supply issues and use excess surface water or treated wastewater effluent as source water. Though driven by declining water levels in regional aquifers, water quality issues are a significant component of each of these projects. The recharge example is from Maricopa, Arizona, at the Water Management and Conservation Research Unit. The project is led by Dr. Clinton Williams and has used treated wastewater effluent to recharge aquifers through a recharge basin since 1998. The project has recharged 40,000 acre feet and has taken the depths of groundwater from 168 feet below ground now to 145. Collaboration is a key component of the effort and includes partners from the city of Gilbert, Arizona, Arizona State University, and ARS. Like the project in Arizona, none of this work is being done solely by the ARS units. Rather, every project described is a collaborative effort of many entities, some including commercial growers, commodity boards, state and federal agencies, universities, and private companies. All are working together to tackle the very real threat of aquifer decline in their regions. With that broad overview of partnership and collaboration, we now shift to a brief review of the science and management tools section of the vision with David Archer, research leader at the Northern Great Plains Research Laboratory in Mandan, North Dakota. David?
Thank you, Michelle. So the overall vision for the science and management tools is getting our science to the users, and that recognizes the need to include the sociocultural and economic considerations and to make best use of available technologies in providing user-focused decision tools. And that includes delivering research in useful and usable tools for use by other researchers to further advance water resources science, and also for use by decision makers to better manage water resources. There's 4 components that our team identified related to that. The first is maintaining a focus on user needs, and that starts with identifying the relevant users at the beginning and then involving those users throughout the entire tool development process. ARS has a long history of developing tools. They've developed hundreds of tools over time, but often they're not always accessible. So we want to maintain a repository of existing tools and include new tools as they are developed in this repository and make sure that they're accessible to the users and easily able to get to them. The next component is identifying the gaps, the needs, and the barriers related to management tools. So that's assessing the need for new tools. Are there any gaps in existing tools? And this includes assessing tool needs for emerging agricultural systems as agricultural production continues to change over time. The second component is identifying the barriers to adoption of these tools and finding ways to overcome these barriers. And the next item related to that is really the integration of these tools with real-time data networks. And that relates to the final bullet there of building capacity to share data and technology and building that capacity to utilize big data approaches. And so this integration with real-time data networks is a part of that. An important component of building this capacity is developing public and private partnerships to facilitate data availability. And then the idea of utilizing a modular design and open source development wherever we can and better able to share our tools and link tools with other tools in decision making. So with that in mind, next slide, just a brief example of one such tool. The Soil and Water Assessment Tool, or SWAT, is a river basin scale tool. It's a continuous time model designed to predict the impact of land management and climate on water, sediment, nutrients, and agricultural chemical yields in watersheds. And SWAT has proven to be an effective tool for assessing water resources and non-point source pollution challenges for a wide range of scales and environmental conditions all across the globe. Currently in the US, SWAT is being used to develop strategies for water quality issues in the Chesapeake Bay, in Western Lake Erie, and in the Gulf of Mexico. And while it's directly used for water quality modeling, it has had many applications to include economic and social linkages and impacts. ARS has a leadership role with SWAT, but the SWAT code and associated software development is a joint collaboration of numerous US and international universities and federal laboratories. And that collaboration extends not only to development, but also to users as well. And so the SWAT team has engaged a wide range of users through the use of online user groups, formal training, technical support, and working directly with users to help customize the model for their own applications. Over time, SWOT has undergone continuous improvement. It has incorporated science advancements as they occurred, and there's been this move toward modular design to accommodate future improvements. There have been improvements to make the model easier to use, and this includes making inputs easier to generate and obtain. And as I mentioned, the SWOT team has worked with many users to make modifications to meet needs for specific analyses. For example, integration with economic and policy models, or including feedbacks and adaptive management and economic impacts that way. So with that, Claire Buffalo, research hydrologist with the Cropping Systems and Water Quality Research Unit in Columbia, Missouri, will provide another example of this continuous improvement in presenting the vision for the research approach. So I'll pass it to Claire.
Thank you, Dave. Our research approach wants to capitalize on our strong point and remain on the cutting edge. One of our strong points is that we have research processes that are diverse, adaptive, collaborative, targeted, integrated, and relevant. To keep it that way and to remain on the cutting edge in the next 30 to 50 years, we need to make full use of technologies, and we need to integrate interdisciplinary approaches in our research process. Next, please. To capitalize on those assets and move forward, we have a vision to remain relevant by developing both long-term research and our ability to address short-term critical issues. We want to develop research goals and agro-ecosystem performance metrics that serve our stakeholders so that our impact will be increased. We want to work with industry leaders to develop new sensor technologies and develop automated monitoring approaches, including data processing methods. We want to share data and tools in effective ways that includes quantifying and reducing the data uncertainty so that others can use those data effectively. Integrate artificial intelligence, machine learning, and data network in our approach to get at problems that have remained intractable so far. The strength of ARS is the wealth of our data collected at local scale, plot or field. With artificial intelligence, machine learning, and spatial analysis methods, we envision scaling those results to broader areas. All of this together will increase our ability to improve decision-making for farm operators, landowners, and land managers. So let me take the example of the National Agroecosystem Model, or NAM, which is led by Dr. White in Temple, Texas. It is based on SWOT+, which you just heard about it. And this model simulates water quantity and quality on the millions of individual fields that are in the US. It also routes water and constituents through the networks of streams and can provide answers at the outlet of any watershed. Thus, it is a very useful tool to scale the results from the field to a river basin. Currently, it is based on national data sets, both for input of the model and for validating the response of the model. In our vision, we expect that artificial intelligence and machine learning techniques, along with multiple data networks, will help ground the model with measured data to provide answers with greater confidence. In our research vision, we have identified some aspects that probably we need to work more on. One is to foster engagement with all of the actors, researchers for interdisciplinary research, industry partners for technology development, and the public for staying relevant, and for land managers to accept our research findings when making decisions. And we want to engage with industry partners to go beyond the publication and the field day for outreach methods and integrate our research findings into applications, practices, and decision tools. So this concludes my review of the research approach section. Next, Dr. Martha Anderson will introduce the water science focus area within ARS.
So the water science section of the vision document highlights 4 general topic areas of research relating to crop water use, water scarcity and excess, groundwater surface water connections, and water quality. Under the topic of crop water use, the focus is going to be on finding means to sustainably intensify our production under constraints of sometimes increasingly limited freshwater resources. Next slide, please. One of the keys to better crop water management is better measurement. And this is one of the goals of the GrapeX experiment, which has been supported by USDA and also by NASA Applied Sciences. So GrapeX is led by Bill Custis, who's at Beltsville, Maryland. It involves a wide range of scientists from industry. We're working with E&J Gallo Winery. We're working with NASA and scientists from other partner academic institutions. The main goal of GrapeX is to develop some new vineyard irrigation strategies that will save water while hopefully maintaining and maybe even improving grape quality for wine production. The experiment also includes some fundamental research on turbulent transport and infection in structured row crops. We have viticulturalists, plant physiologists looking at signals of vine stress that can be related to the remote sensing data. The focus of GrapeX really has been mostly on vineyard systems to date, but the tools and the methods we're developing are pretty generic. So more recently, we've been expanding into other irrigated crops, irrigated nut orchards, almonds, and this is under the partner project, T-Rex, which is being led by ARS scientist Andrew McElroan at UC Davis. There is a YouTube video. I don't know if it's still listed there, but we can put it in the chat if you want to get more information about GrapeX and T-Rex. Next slide, please. So water scarcity, that's a timely topic given the mega drought that's occurring in the Western United States right now. The informational requests that we're getting about this drought and other droughts are trending towards finer and finer spatial resolution down to field and subfield scales, lower temporal latency. There's a need for real-time information and better seasonal outlook. So this is going to take some new remote sensing and modeling techniques to really get down to that field management scale and also to develop better, more localized forecasts of these weather extremes. Future research in ARS is also going to be aimed at better understanding the linkages and the flow paths between our ground and surface waters, as well as the impacts of irrigation on these water levels. There are new geophysical remote sensing techniques that can be used to infer the subsurface structure to better identify and delineate flow paths connecting the surface and the water table. And studies like those, technologies like those are going to be really important, for example, in siting areas for managed aquifer recharge experiments, as we heard about earlier. And then finally, ARS research will continue looking into new practices, new technologies to reduce the impacts of agriculture on our water quality. An example of this are ARS scientists in Florence, South Carolina, that have developed a really innovative new system for treating water in a swine manure lagoon. This system cleans the water and it also transforms the phosphorus that's recovered into usable liquid and solid fertilizer. So that technology has great promise if it can be adopted on scale. Next slide, please. So in ARS, we have been researching these topics for a number of years now. The partitioning of topics in our 5-year action plans has kind of evolved through the years, as you can see in this timeline here. Back in the earlier days, the research tended to be a little more siloed with individual groups working more independently. But recently this has kind of started to change as we're evolving towards a more interdisciplinary and a more transdisciplinary approach to our research. And with that, I'm going to hand it over to Kyle Mencken, who is the research leader in the Water Management and Systems Research Lab in Fort Collins, Colorado.
Thanks, Martha. So transdisciplinary science is where things get messy and exciting, and it's central to how we need to solve critical water challenges. When we talk with stakeholders about the real world challenges they're facing, they're rarely solved by one scientific discipline or one research project or even one agency. The solution needs research to span water resources and water quality and technology, remote sensing, AI, genetics and economics, and several areas of agricultural and natural resource sciences all at once. And this ARS research needs to connect with and build upon the expertise and resources of other USDA agencies and universities, the full breadth of federal science and action agencies, local government, industry, and others, so that we can nudge the dial. Next slide. So as an example, a glimpse of our approach to transdisciplinary research, take a look at the science-based cover cropping programs of the Chesapeake Bay. This slide shows how agronomic cropping system studies, GIS-based targeting technologies, water quality monitoring in the field, and estuarine limnological research was all needed to create new effective solutions. This wasn't just an ARS project. We worked in concert with other research institutions like land-grant universities, USGS, NASA, EPA, NOAA, to develop the science that was promoted by other federal, state, and local action agencies through their subsidized cover cropping programs, and ultimately credited with major improvements to bay nutrient loads. Together, we nudged the dial. Our vision would expand this type of transdisciplinary approach of research, outreach, and action to other challenges. This isn't your grandmother's cookie cutter approach. We're going to need new research, new collaborations, and new approaches to deal with each challenge. Next slide. I kind of like this slide. ARS research is starting on the left in red in 2021 with every possible challenge to water research by the growing global demand for food and water, both in terms of water availability, too much, too little, or not at the right time, and water quality, where agricultural can be both the problem and the solution. Over the course of the year that we've worked on this vision, I was both impressed by how much ARS is already doing on all these water research issues, and perhaps a little frustrated by the difficulty we have in showing that our research is nudging the dial. So while we spent a little time in the crystal ball trying to guess where we'll be in 2050 on the right in blue, we probably spent more time thinking about that messy, iterative, transdisciplinary research place in between. How do we get there? So the next slide. Briefly, from all the previous speakers, that's our vision. USDA ARS is a leader in water research and a hub of water research partnerships. And together we must frame the research needed to solve critical societal level challenges, leading to sustainable research outcomes, new innovations, and transdisciplinary interagency approaches that solve those challenges. But like I said, we're still working out the how. And these persistent challenges are not something that ARS or any one agency or organization can tackle alone. Among our goals over the next few days, I think, is together to brainstorm questions like what critical water research challenges should we be working on together? How do we avoid overlapping effort or reinventing the wheel? How do we break down internal and external barriers that keep us from building partnerships? And kind of fundamentally, how does our research vision that we're talking about here help you accomplish your vision? We're really looking forward to hearing your thoughts and ideas on our vision, and importantly, how we best use ARS water research to get there. So now I'll hand it off to Emily Elias, research hydrologist and director of the USDA Southwest Climate Hub. Emily.
Thanks, Kyle. I'm also a member of the editorial team for this Water Research Vision to 2050, and I'm really looking forward to hearing your feedback and to envisioning some collaborative efforts with you. So before we move into our breakouts, I want to take a moment to let you know how to give feedback and how the feedback will be incorporated into the vision. There are two ways to give feedback. The first is in the breakouts. We'll be capturing the chat feedback in all of the breakouts. So if there's something you really want to say or include, feel free to use the chat box. We also have a scribe in all of the breakouts that will be capturing the high-level themes. Another way to provide feedback is via the Google document that was hosted and sent to you by Gilberg Leadership Incorporated, and you can enter your feedback directly into the summary vision document. After the workshop, we'll synthesize the feedback into a partner feedback paragraph for each section of the vision. So each of the presentations you just heard, we'll synthesize the feedback there. We may also add another section at the end of the vision to highlight collaborative efforts that may result from our discussions over the next 3 days. Then in the next few months, we'll publish the vision summary with your partner feedback. We'll also submit a peer-reviewed publication to Nature, update a draft website that we have for the vision, and then send to you, all of the people attending, a collection of slides documenting the ideas that are shared during this virtual workshop. So with that, I'll thank you again for being here, and I'm looking forward to hearing your ideas.